Hello, everybody. Welcome to the seminar series, Science with QuEra. I'm your host today. My name is Alexei Belinsky. I'm VP of Quantum Computing Services at QuEra. Today, we'll tell you about quantum simulation of lattice gauge theories and the observation of string dynamics in these theories by two separate teams on two different quantum processors. One is QuEra's analog quantum computer, Aquila, based on neutral atom qubits, and the other one is Google's digital quantum computer, Sycamore, based on superconducting qubits. With me, I have the teams that did this work from the Google collaboration. We have Bernard Jobs from the University of Munich and Tyler Cochran, who is actually currently at QuEra. From the QuEra and Innsbruck collaboration, we have Majid Hamdan from QuEra, and we have Daniel Gonzalez Cuadra, who is now at the Institute of Fundamental Physics in Madrid. Before we jump into the science, I do want to share a few words about QuEra, the host of the webinar series. We are located in Boston, and we are in very tight collaboration with Harvard and MIT, the labs that pioneer neutral atom research, and the various techniques to build neutral atom quantum computers. At QuEra, we're a team of over 50 scientists and engineers, and we develop and commercialize computers based on neutral atoms, both the analog and the digital mode. And the analog mode was what you'll hear about today from the QuEra side, and of course the digital mode will what you'll hear about from the Google side. We have made Aquila accessible on Amazon Braket via a cloud service to the world in November 2022, and it has been operating since. And actually, this year, we have our first on-prem installation of a machine at the AIST in Japan. And incidentally, that machine is also our first generation gate-based quantum computer. So with all of this, we try to partner with enterprises, HPC centers, and governments in their quantum journey as part of our business model, and to provide full stack services. So that really means the ability to meaningfully use quantum computing on real hardware, but with the help of software integrations, software tooling, and even professional services. We recently received a $230 million investment led by Google and SoftBank to accelerate our journey to fault-tolerant, scalable, and useful quantum computing. And this seminal work on string breaking, we think of as one of the milestones in this journey towards making quantum computers truly useful to various fields in science and hopefully one day business. With this, I will turn it over to Daniel for our scientific program.
Thank you, Alexei. Just 1 second. Okay. So yeah, hi everybody. Thanks, Alexei, for the nice introduction. So I will start with some general motivation behind this work. So why do we care about simulating gauge theories? So the short answer is that gauge theories form the framework behind the standard model of particle physics. So here I'm showing some sketch of the phase diagram of QCD. This is quantum chromodynamics. This is the sector of the standard model that deals with strong interactions between quarks that are mediated by gluons, that are the corresponding gauge bosons of the theory. So the physics of QCD is normally proved experimentally in particle colliders, for instance, at CERN, where they smash heavy ions, for example, at very high energies, to try to reproduce different parts of this phase diagram, measure the particles that are produced, and then trying to advance in these questions and understand this physics a bit better. The problem is that for that, we need to make first principle calculations from QCD that we can compare to the experiment. And this is computationally very challenging. So there are different regimes that are very hard to access with classical computers. So for instance, large baryon densities, but also non-equilibrium dynamics. So this is the reason why we want to use quantum simulators to try to study this type of theories from first principles. Of course, if we want to simulate QCD, this is a very complicated problem. For that, we will eventually need error correction, fault-tolerant quantum computing, and so on. So the question is, what can we do with near-term devices that already allows us to study this type of physics in regimes that are challenging from a classical point of view? So in this seminar, we're going to present different works that study one particular phenomena that appear in these theories that's called stream breaking. So quarks, as described by QCD, are always connected by these strings. So these are excitations of the gauge fields of the gluons that mediate the interactions. And the interactions in QCD are such that when you try to pull these quarks apart, the energy will grow linearly with the separation. So this is different from the Coulomb law, for instance, in electrodynamics, where the energy just decreases with the distance. So in this case, it increases like a spring. So when you try to pull these quarks apart, at some point this string can break by producing particle pairs from the vacuum. So this is something that happens in these heavy ion collisions, for instance, in these particle colliders, where these ions pass through each other. So then these quarks interact, the string between them gets elongated, and at some point there is so much energy that you can produce these particles from the vacuum that then you can detect in this collider. So the nice thing about this phenomena is that it does not only occur in QCD, but also in more general gauge theories that are simpler to simulate, but still hard to do classically. And this is the phenomena we are going to focus in here. So this the framework that we are going to use for that, it's what's called lattice gauge theories. So this is a framework in which space is discretized in a lattice, and then we place our fields in this lattice. So the matter fields that describe quarks, electrons, and so on, we place on the vertices of the lattice. And then the gauge fields, so gluons, photons, and so on, that mediate the interactions, they are going to be placed on the links in between sites. So the important feature about this type of theories, and hence the name, is that they are invariant under gauge symmetries. So these are local symmetries. These basically give rise to local conservation laws. So one example is the standard Gauss law of electrodynamics that basically connects the divergence of the electric field with the charge that is at a single point in space. And more, let's say, complicated versions of these constraints also appear in other type of gauge theories, but the structure is similar. So this basically constrained a lot the type of physical states that appear in these theories. In particular, as I said before, when we have these pairs of quarks, they always have to be connected by these strings of gauge field excitations. So this is one important ingredient that we want to implement in our quantum simulator. And then there are other ingredients. We need some sort of confining potential, such that the energy will actually increase with the distance between quarks. We'll need some sort of mass for the particles, so there is some interplay between the energy of the string and the energy of the particles. And then finally, we need some gauge matter interaction to actually produce these pairs and break the string. So there's been a lot of early experiments in the last years performing quantum simulation of gauge theories, mostly based on ultracold in optical lattices and also trap ions. So they work either in an analog mode, in which you really design your system such that the Hamiltonian of this gauge theory emerges, or you use a digital approach in which you use quantum gates to build the unitary that it's required to simulate the dynamics under the Hamiltonian you're interested in. So in this case, a gauge theory. Most of these works have focused on small systems, and in particular in 1D. And it's pretty challenging to use these kind of devices to scale to higher dimensions, in particular to 2 dimensions. And this is what we are going to focus in this webinar. So we are going to explain these recent experimental results from Google and QuEra that were the first large-scale quantum simulations of gauge theories in 2D. And the reason why this is important is because this is the regime where actually classical simulators struggle. So if you want to simulate the dynamics of 2-dimensional systems, this is actually very hard. So as I said, we are going to explain what Google did using superconducting qubits. This was a digital approach. And also what QuEra did. This was an analog approach using read atom arrays. And the nice thing is that this is very complementary. So these are different type of hardware. Also, the protocols for quantum simulation are different, digital and analog. The type of theory was also a bit different. In one case, a Z2 gauge theory, and in the other case, a U1 gauge theory. But in both cases, they target this phenomena of string breaking. Since I participated in this QuEra experiment, I will start with this one. So these are based on the results on this article that was published 2 weeks ago in Nature. And this was a collaboration that was done between the group of Peter Soller in Innsbruck, where I was as a postdoc back then. So we did the theory part, also together with Michelle looking at Harvard, but also mainly with QuEra, where the experiment took place. And here Majid, that we'll talk later, was the main person behind this experiment. So let me explain the theory behind this approach. So Rydberg atoms can be trapped in optical tweezers, which are tightly focused laser beams, and can be placed in any desired geometry. The interesting feature about them is that we can excite them to Rydberg states that are highly excited electronic states with a large dipole moment. So when two atoms are simultaneously excited, they will interact very strongly via van der Waals interactions. Actually, interaction is so strong that they give rise to the so-called Rydberg blockade mechanism. So what this means is that if one atom is excited to this Rydberg state, there is a whole area around in which no other atom can be simultaneously excited. And the reason is that if there is another atom there, also excited, the interaction energy is so strong that basically this energy penalty that is effectively, so these states are effectively removed from the dynamics because it costs too much energy. So one can understand this blockade constraint as a local constraint. So we can interpret this as this gauge constraint that appear in these gauge theories. So this is something that people realized already some years ago, that, for instance, the 1D PXP model that described the Rydberg system in 1D can be mapped to a U1 lattice gauge theory, and actually the phenomenon of many body scars were also interpreted in this language. This is something that it's also the case in 2D. For instance, there was also a recent experiment with Rydberg atoms where they observed a spin liquid that can also be interpreted as the deconfined phase of a lattice gauge theory. But here we are interested in confinement. So this is kind of a different phase of the gauge theory. So for that, as I said before, we need something else. So we don't need only this gauge symmetry, but we also need a confinement potential. So let me show you how we get that. So what we did in practice is the following. So we took an hexagonal lattice, and then we placed the atoms in tweezers on the links of this hexagonal lattice. So here I draw these Rydberg excitations in color and the atoms in the ground state in white. So if now you consider that an atom is excited to a Rydberg state and that the Rydberg blockade radius is one lattice spacing, there will be this basically area where no other atom can be simultaneously excited. So these 4 atoms cannot be excited to the Rydberg state. So in this limit, in the blockade constraint limit, one can recast this constraint in this equation here. So basically, for each side of this hexagonal lattice, we can write the following. So the sum of Rydberg excitations on the links that are connected to this side, they have to be either 0 or 1, but cannot be 2 or 3, because that's not allowed by this constraint. So in this form, this can be actually written very similarly as the Gauss law that I mentioned before. So one can interpret these Rydberg excitations as an electric field, and then write this sum of excitation as a divergence of such an electric field, and then the fact that we have either 0 or 1 excitation can be also interpreted as a charge, as the matter content of the theory. So actually one can make this formal and map, so there's a one-to-one mapping between configurations of Rydberg excitations that follow these constraints, these local constraints, as the states of a lattice gauge theory with a U1 local symmetry, where we have these charges on the sides and this electric field, that are U1 electric fields on the links. So the exact mapping is not so important, but maybe something that you should remember is that we define this in such a way that this order configuration here of excitations, you see that they follow some order pattern, this will correspond to the vacuum of our theory, And then the effects on top of this order configuration will be our charges and our strings in our gauge theory picture. So with that, we can actually write the Rydberg Hamiltonian as a lattice gauge theory Hamiltonian in this regime, where we have first a gauge matter interaction. So basically we have hardcore bosons in this case that can hop between different sites, but this tunneling is always mediated by the gauge field that in this case is represented by these spin 1/2 operators. Then we also have a mass term in the Hamiltonian that gives mass to the matter, and this can be modified just by changing the detuning. And then finally, we have an electric energy term that's a bit ugly, so this comes from the long-range nature of the Rydberg interactions, but I will explain just in a second that this is the one that gives rise to this confinement potential. So let me explain this a bit more in detail. So something that's important to notice is that, as I mentioned before, Rydberg interactions decay as a van der Waals potential, so they depend on the distance with this power law here, so there is long-range interactions. So that means that in the limit of large detuning, we want to have as many excitations as possible, but they have to follow this constraint, and also the distance between this excitation has to be as large as possible to minimize this van der Waals potential. And that's why in the ground state, for a large range of parameters, the ground state of the Rydberg Hamiltonian in this geometry actually has this order pattern. And that's why we define basically our gauge theory vacuum in such a way. But then on top of that, we can have defects. We can have defects on this order configuration. And this is, as I said before, what corresponds to our charges and our strings. So for example, we can have sites in which there is no Rydberg excitation around. This is a charge. Similarly here. And then the atoms in the middle, there is this 1D defect where the excitations get displaced with respect to this vacuum pattern. And now the key feature is that this has an energy cost that increases linearly with the distance between the charges. In order to understand why this is the case, so this is kind of easy in a semi-classical picture. So when you're in the vacuum, Rydberg excitations don't interact to nearest neighbor due to the blockade, also not to second neighbor, this is also 0 here, but third neighbor has an energy contribution. However, in the atoms in this defect, in this string, they already interact at the second neighbor. And that's why when you make this string longer and longer, there is an energy contribution that is proportional to this second neighbor interaction. So you can tune it by changing the Rydberg interactions, and this will grow with the length of this string. So now we have all the ingredients that we want. And the nice thing is that this emerges from our Rydberg array without having to do any engineering. So we really just put the atoms on this geometry, and in the right parameter regime, we get a gauge theory with this confining potential. So now we can study stream breaking. So what is the stream breaking condition here? So basically, the energy of the string, as I said, depends on the distance between the charges. And then when that energy is equal to the energy that it costs to create a pair of particles from the vacuum, and this depends on the detuning, also with some renormalization factor that depends on the long-range tail. When this condition is met, then this process is resonant. So we can break the string by creating particles. And you can see that here, these are DMRG pictures showing what's the ground state of the Rydberg Hamiltonian in certain parameter regime. And you can see how if we put charges at a certain distance, there will be a stream between them, but if we separate them at some point, this stream breaks and there is dynamical charges that are created to break the stream and to screen the initial charges that we put in. So this is the theory behind this analog quantum simulation approach. And now I will let Majid continue and explain you what are the experimental results on this side.
Thank you, Daniel. I'll take over now and speak a bit about the experiment. So we start our study by considering Kagome lattice of Rydberg atom with 5-unit cells in the x direction and in the y direction. So the first figure here shows the broken string arrangement on our lattice. So when we go to 2 dimensions, the string can take different paths to connect the charges. So here I am showing the strings with the minimal length labeled 1 to 6. So the claim of our mapping is that the ground state of the Rydberg Hamiltonian on this lattice and in the ordered phase should be either the broken string arrangement or a superposition of the string arrangements, depending on the relationship between the mass of the charges and the string tension. We can confirm this by theoretically computing the phase diagram of the Rydberg Hamiltonian as a function of mass and string tension. Here, the z-axis shows the probability of the string subtracted from the probability of the broken string. As expected, we see two distinct regions in here, where we observe the string and the broken string. So in the string region, I'm plotting here the collective probabilities of the 6 strings, and the black dots over here shows the order phase where our mapping holds true. So experimentally, we realize the ground state of a quantum system using adiabatic state preparation protocol. So we start at large negative detuning, where all the atoms are in the ground state. Then we enable interactions between the atoms by ramping up the Rabi drive. And as we do that, we sweep the value of detuning very slowly until a final value of detuning for which we want to know the ground state of the system. So now by scanning the final value of the detuning and the spacing between the atoms, we can recreate the theoretical phase diagram. So here are the experimental results. As you can see, there are 2 distinct regions within the ordered phase, consistent with the theoretical prediction. I'm also showing pictures of atoms from the experiment. And for the string case, I'm only showing a picture of one of the 6 different string arrangements. So to resolve the dynamics of string breaking, we start by preparing a string state, quench the system to conditions that break the string by either decreasing the mass or increasing the string tension, and then observe this process as it happened. In our experiment, we increase the string tension by adding a locally tuning pattern that energetically promotes the broken string state. This effectively adds a linear contribution to the string tension coefficient. Experimentally, we do this using adiabatic sweep to prepare the string state. Then we follow by a quench and locally tuning, which takes the system from all items being in the ground state to the string state and finally to the broken string state. And then if you scan the quench magnitude and the duration, then you can watch the system undergo the dynamics in different conditions. So our system has a finite coherence time. So the adiabatic sweep we're using in this case has to be shorter than the one we used in the phase diagram to allow for enough time to quench. This effectively makes the adiabatic sweep less effective at making the string state. So to obtain meaningful string probabilities, we had to reduce the system size and explore the dynamics in the 1D case. So we consider a system with 5-unit lattices in the x direction and 3-unit lattices in the y direction. So we should expect that when the quench magnitude is 0, no string breaking will happen, and the probabilities of the string and the broken string should remain the same. So this is confirmed by data. Here the x-axis is the quench duration, and the magnitude of the quench is shown on top. We can see here a small decrease in the probability of the string as time goes on. We attribute this to decoherence at longer time, and we explain this in details in the paper. So when we increase the value of the quench, we see strong decay in the probability of the string, as well as a simultaneous growth in the probability of the broken string. Now, if we push the quench to even higher values, we see an even stronger decay in the string probability, but a smaller growth in the broken string probability. But from this data, it seems that the magnitude of the quench plays a role in determining the final broken string population. So we can understand this relationship between the two better if we look at a spectroscopic measurement of this data. So next, I will show a plot of the broken string probability only at 0.4 microsecond as a function of quench amplitude. So interestingly, the broken string probability maximizes, then decreases as we increase the quench amplitude. This is usually an indication of a resonance phenomena. And one way to understand this is to interpret string breaking as a higher order coupling process. So if we think about it, multiple atoms have to flip from ground to Rydberg and from Rydberg to ground in order to move from the string state to the broken string state. The chance that all of them flip at the same time is quite small. So even when the mass of the charges is equal to the string tension, the coupling between the two states is small. And this coupling can be mediated through the intermediate transition state I'm showing here, where the flips will happen and emerge sequentially. So one of these states is a fully charged state. I'm showing its probability in blue. you can see that it goes through a similar behavior than the broken string state, but it maximizes at a different energy value. Now, in this interpretation, these different states have specific energies. The string energy has the lowest the string state has the lowest energy. And as we increase the quench amplitude, we increase the string energy. When this energy is equal to the broken string energy, we're only limited by the coupling to that state. So that's when the probability maximizes. And as we quench to larger values, the energy of the string becomes resonant with a fully charged state, where we also see a peak. So we can confirm this by computing the classical energies for each one of the string and exact numerical predictions based on this interpretation. So we see that the classical string and the broken string cross around a value of quench of 1, which agrees with the theoretical prediction and is within a line width of our experimental data. Now, as we scan the string tangent to larger values, the string and the fully charged state cross around a detuning value of 2. As you can see, this doesn't agree with the experiment or with the theory. This is because the energy gaps around the fully charged states are smaller compared to the broken string state, explaining the displacement of the peak with respect to the classical data. And now, one final thing we can do to confirm that this interpretation is to study it on longer string. For longer string, the string tension is higher, which means the energy of the broken string and the string are actually closer. So we should see this peak move toward the left. Now, as data show, this is indeed the case. Here I'm showing the data for a string of 3 units compared to the string of 2 units I was just showing. So you can see here that both the experiment and the numerical data show a reduction of resonance peak by about 30%. The classical shift, however, is about a 2-factor larger. So I hope that this agreement between the experiment and the numerical results and their deviation from the classical model can show you how necessary it is to use quantum simulation to understand quantum features of SVT. As you can see, classical predictions fail for small systems very quickly, and numerics will start struggling with computation complexity as we go to larger systems, which leaves us with quantum simulations as a solution for larger systems. So this concludes our presentations on the analog simulation, and now I will leave it to the Google team to speak about the digital simulation.
Yes, thank you. I'll introduce our simulation or digital simulation of a lattice gauge theory that we run on Google's superconducting quantum hardware. Sorry. Yeah. So this is a result of a large collaboration with many different people involved, the main people of which are shown on this slide here, with the team from Google Quantum AI mainly focusing on the experimental realization and actually running these circuits on the hardware, and then teams from the Technical University of Munich and from the University of Nottingham working on the theory side of things. So in our experiment, we considered a Z2 lattice gauge theory. So this consists of having qubits on the links of such a square lattice as shown on the left. And we can think of the 2 states of the qubit for the gauge field as really just representing whether there is an electric field line present or if it is absent. And then we also have meta degrees of freedom, which live on the vertices of such a square lattice. And there are also 2-dimensional degrees of freedom, which just indicate the presence or the absence of a charge. So these 2 fields are then coupled, as was said before, by a Gauss law. So essentially, if we have an electric field line somewhere, then this must always terminate at electric charge. So for example, if I consider such a line of flipped qubits as here, which represents such an electric field line, if I have an even number of field lines meet at a vertex, this means that I don't have an electric charge, and essentially the electric field line just passes through the side. But if I have an odd number of electric field lines meet at a vertex, that means that one of the field lines ends here, and I must have an electric charge there. And so this relation between the gauge field configuration and the electric charge allows us to simplify the problem a bit. We can essentially get rid of the meta fields explicitly by just fixing a gauge. So I want to stress that this is different from considering a pure gauge theory without dynamical matter fields. In our implementation, we do still have dynamical matter fields. It's just that we fix a gauge to make the problem a bit simpler. And once we have fixed the gauge, the problem reduces to the Hamiltonian shown here in the top right. It's essentially just the toric code in a field. So the first term in this Hamiltonian just checks how many field lines end on a certain vertex, and from this it infers whether there is an electric charge present or not. If there is an electric charge present, this gives an energy penalty, so this acts like the particle mass term of our theory. The next term just measures essentially the magnetic flux through a plaquette, so it gives the energy contribution of the magnetic field, and this is also the term which is then responsible for giving dynamics to these electric field lines. The third term just locally measures whether I have an electric field line present or not, and it gives an energy cost to having an electric field line there. So this just measures the energy of the electric field. And this is in the end, if I tune the electric field coupling strength, this is what leads to this confining potential. And finally, we have a minimal coupling between the gauge fields and the matter fields. So this essentially just flips or changes the gauge field configuration such that if on this link I had a neighboring electric charge sitting there already, then this one will hop effectively. But if there were no neighboring electric charges at the vertices, this will create a new pair of electric charges. So this is the model. And since we have a digital implementation of this lattice gauge theory, we essentially have access to the full parameter regime of this theory. But we will mostly focus on this lower region in the phase diagram, where we can then tune the electric field coupling strength. So for small coupling strengths, we essentially just have a perturbed toric code, and we recover the physics of the toric code with its deconfined excitations and the string connecting these charges, essentially costing no energy. Now, as we tune up the electric field coupling strength, the string that connects two charges that are far apart, this will get an energy cost. So if I have two charges far apart and they will be connected by some electric field line, this electric field line will cost a lot of energy, and this configuration will be unfavored. So this drives a transition to this charge confined phase. So typically, we think of this confinement or defining confinement as this sort of static setup where I put two charges in my system, and then I want to ask, what is the energy of this configuration as I take these charges further and further apart? But I can also think of this as a dynamic process. So if I put in two charges into my system and I just let it evolve with the Hamiltonian of the deconfined phase, then essentially these two charges should just individually spread out over the lattice. But if I evolve the same setup in the confined phase, then the string that connects to these two phases acts kind of like a spring that pulls these particles together. And I can see an oscillation of these charges around the equilibrium position, and also I should be able to see the vibration of this, essentially the spring connecting these two charges. And if you're already in this confined phase where I have the string connecting the two charges, which acts like a spring, we can also tune up now this gauge matter coupling, which increases the rate of pair production. And if this pair production happens on top of the string, we can see the string dynamically breaking. So in contrast to this analog simulation of gauge theories, we don't prepare our initial states by some quasi-adiabatic protocol, but rather we get to design a circuit to really have the initial state that we want. To get this initial state, or to construct this initial state, we're also guided by the connectivity of our qubit grid. So we're using Google's Sycamore processor, which is a square grid of superconducting qubits shown on the left here. And the green diamonds represent the gauge qubits, which carry the degrees of freedom of the gauge field. So they're the physical degrees of freedom that we're interested in simulating. And there's also a bunch of gray circles representing ancillar qubits that we use to essentially facilitate the Trotter steps for simulating the dynamics. There's also some blue circuits which correspond to another set of ancillars, which we use for implementing a Hadamard test to be able to get access to two-time correlation functions. So the circuit that we end up using is essentially just the circuit that prepares a toric code state, except that we replace the first single qubit gate in this state preparation protocol by a parameterized rotation gate. So the idea of this circuit is essentially that these C-knots that act around the plaquette, they just flip all of the qubits around this plaquette, so they create closed loops of electric field lines, and the product of all of them just gives a superposition of all closed loop configurations. Now for the toric code, without any fields, if all of these configurations have the same weight, then this is the exact ground state. But now as we tune up the electric field coupling strength, these long loops carry an energy cost and actually should be penalized and suppressed to get a low energy state. So we can tune this weight by essentially just tuning this rotation angle. And now it turns out that this state that we choose is actually equivalent to a mean field ansatz for a two-dimensional transverse field Ising model, which is dual to the toric code in a field. So it turns out we can optimize this rotation angle theta for arbitrary system sizes very efficiently, which is also shown here in particular for the thermodynamic limit. And then finally, we can ask how good the state that we prepare is, and we can do this by measuring the energy of this ansatz on the quantum computer and compare it to other initial states which we could have chosen, such as just the toric code or just the fully polarized state where all Q is in a zero state. And as we tune the electric field strength, we see that even on the quantum computer, this ansatz that we take, the circuit that we use, has a much lower energy than the other states. And now for the results of the dynamics on the quantum computer, I'll hand it over to Tyler to present this.
Great. Thanks so much, Bernard. Oh, sorry. Let's fast forward here. Okay, so my involvement with this project was during my stay at Google Quantum AI as a PhD Harbor resident. And in this case, as Bernard was saying, we want to explore the dynamics of these strings dynamically to kind of differentiate the confined and the deconfined regime and look at the string dynamics. So to do that on the quantum processor, we use a Trotter-Suzuki time evolution. And in that process, we break the full Hamiltonian, which is shown here, up into local field terms and the plaquette terms, which are the four body operators, which are these four Z's and these four X's. And so kind of stroboscopically, we first implement the local field terms just with local single qubit gates. And then with a series of four C0 layers, we're able to take this four body operator and put it on the ancilla qubits that are sitting in the middle of each one of these vertices and plaquettes. And then again, just with local single qubit rotations, we're able to implement that Trotterization of these four body terms and then spread the operator back to the physical qubits with another four layers of C0 terms. So, the take home here is we're able to, just by tuning these individual single qubit rotations, implement an arbitrary instance of these Hamiltonian parameters. And this is what we're going to use to explore the dynamics of this model. So as the first example, we can look at the dynamics of two charges. So we start with this variational initial state that Bernard explained, and then we create two initial charges separated by a string of length 1, just by applying a local X gate. And now we're going to measure these A sub V operators on all of the plaquettes or all of the vertices in the system, all of the charge sets. And we're going to do that with these Hamiltonian parameters with a weak H sub E term and a strong H sub E term corresponding to where we expect deconfinement for small H sub E and confinement for large H sub E. And here are the results from the experiment. We see that, as you would expect, in the deconfined regime, these charges are kind of spreading quickly to spread out over the grid of charge sites. But they seem to be spreading less quickly in the confined regime on the right, which H sub B is equal to 2.0. If we want to be a little bit more quantitative about this, you can actually measure the separation between two charges. And we see that when we take that as our expectation value, indeed, the charges are spreading much less quickly for the confined case, for this large H sub B case. But maybe unintuitively, they're still spreading as a function of time, roughly linearly. But you have to remember that the longer you evolve in time, that means the more Trotter steps, that's the more total gates that you're doing on the quantum processor. And each one of those gates is incurring some amount of error. So there's some sort of decoherence mechanism that's happening more and more and more as you go to later and later times. So we can get a handle on how much decoherence is happening actually by evolving with lambda equal to 0. In that case, these A sub V operators actually commute with the entire Hamiltonian. And so we expect kind of stationary dynamics. We expect these charges not to move. But this kind of gray bounding region here shows that even under those parameters, we see these charges separating. And this is just coming from the decoherence on the device. So we can rescale our data I'm just assuming a global depolarizing channel, a very simple assumption, but then we get very good agreement with the exact circuit simulations, which is what's shown here in this bottom panel. Okay, so now that we have a handle on the confinement and deconfinement dynamics of the charges, we're interested in exploring these strings. So we start with an initial configuration now of two charges that are kind of stretched to the edge of our system and a string that are connecting them with the bunk. And we're going to measure this S sub ZZ of T observable, which is the product of a two-time correlation function and the expectation value of Z on all of the qubits at the initial time. So to do the first part, it's quite easy. We just prepare the initial state and we measure. What we see is exactly intuitive. The qubits where the string exists have a negative value of Z, and where the string doesn't exist has a positive value of Z. And then to measure this two-time correlation function, as Bernard mentioned at the beginning, we use this Hadamard test. And the basic flavor of what we're doing here is that before we do the time evolution in the circuit, we kind of store the information on one of these blue ancilla qubits sitting on the edge, and then by jointly measuring the ancilla qubit and the system qubit after the time evolution, we're able to kind of construct this two-time correlator. So what are the results? We see in the deconfined case, there's really no there are no coherent string oscillations, or fluctuations at all, which is what we expect. In the deconfined case, in the weakly confined case, we see a lot of interesting sorts of fluctuations happening. There are kind of breathing modes where the string is exploring these outer sites, and it's also flopping over to the bottom qubits. But when we increase the confinement even more, we suppress these sorts of flopping over to the bottom oscillations, and we really just have oscillations of the string on the top set of qubits. So we're able to really directly visualize the dynamics of the string under these different Hamiltonian parameters. Now, by focusing on the strongly confined case, we're able to also see string breaking. So we're going to keep the string on the top with the strongly confined dynamics, and we're going to now do a differential measurement by measuring the charges that are produced in the lattice by pair creation when I just evolved the initial vacuum state, or the variational state that's a close approximation to the vacuum, and the state with the string that I discussed in the last slide. And the idea is, if we have coherent string breaking, we should expect to have more excitations present where the string is. And that's exactly what we see. So here, red is more excitations from the initial state with the string, and we see that those initial excitations are localized where the string is oscillating on the top. So we can kind of track this as a function of time for different plaquette sites. And by looking at where this kind of pair creation occurs, we're also able to see a resonance condition, which is very close to where the cost of flipping one gauge spin is equivalent to creating two excitations. Exactly this picture here shown in the string breaking cartoon. Great. So yeah, it was a pleasure to present this work that I did with Google Quantum AI alongside everybody at QuEra, and I'll hand it back over to Alexei for questions.
Thank you, Tyler, and Maj, and Bernard, and Daniel. You guys should come up on video for the Q&A period. Just to conclude, I think that this is a great showcase of the discovery work that can be done when you bring theory and experiment, different hardware platforms in quantum computing, and ideas from different fields, in this case quantum computing and high energy physics, together. I hope that all the participants were just as excited about what this kind of work can mean. At this point, I will maybe ask some questions that were brought up in the Q&A. So the first one is related to a discussion that was kind of going back and forth on the generality of these lattice gauge theories that are implemented. So for example, there's different dimensionalities, and then there's different, actual, geometries in which you implement. And the question is, does confinement exist, and does it exhibit the same behavior in these different dimensionalities, and also in the different implementations? And I think Daniel had some good answers, but maybe you can kind of summarize your comments on this.
Yeah. So yeah, as I already wrote in the answers, So I think it's important to notice here that although what we are simulating is a U1 lattice gauge theory, so this has the same symmetry group as quantum electrodynamics, but it is not quantum electrodynamics in the sense that here the gauge fields are truncated. So in QED, you will have an infinite dimensional Hilbert space for the gauge fields, and here we are basically approximating that with two-level systems. So it's a kind of crude approximation. So it's quantitatively very different from QED, but still qualitatively it retains many features. So for instance, confinement and stream breaking and so on. But this, of course, also modify the properties of the theory. And as some people mentioned in the comments, for example, in QED, in quantum electrodynamics, in 3 dimensions, which is what we see in our real world, let's say, the theory is not confined. There is no confinement there. So here confinement has to do with both this truncation, but also with the fact that we are in 2D, which is not what happens in the real world. So this is more like a toy model to capture this phenomena, but it's quantitatively different from what happened in the real world, which is of course what we want to do eventually. But this is more like a first step in that direction.
So maybe I can follow up on what you just said, which is, how do we get to simulating things that are not necessarily even on a lattice, but in continuum, which is, what QCD lives on. And, if you still hope to use quantum computers or quantum simulators for that, how do you imagine the quantum resources scaling with the problem size and with the quality of the approximation to the real world?
Maybe I can also answer that. So yeah, this lattice gauge theory formulation, I mean, this is also what people use for Monte Carlo simulations with classical devices, and this has been very useful for many decades to predict properties of fundamental particles. And also in that case, you need to basically take larger and larger lattices with smaller and smaller lattice spacing, and then eventually extrapolate to the continuum. So with quantum simulators, eventually we'll have to do the same if we want to become quantitative. So we will also have to make larger and larger system sizes. This is also the case in condensed matter if you want to study like thermodynamic limit properties of materials and so on. So this is something that's expected. Of course, the resources will scale with the system size. In principle, we know that quantum simulation is efficient. So in the sense that they will scale polynomially. This can still be like pretty high in the sense of like number of qubits and so on. But it's not, let's say from a complexity theory point of view, it's still under control. So we are hopeful that with fault-tolerant devices, we can eventually become quantitative in the sense of making predictions for the continuum theory.
I'll just say, there are some subtleties as well that, you have to expand the number of qubits when you want to go to larger truncations or like later truncations of the gauge group. And also similar issues will be faced, kind of as Daniel alluded to, in using these models as effective theories for condensed matter systems. So gauge theories are very relevant for high temperature superconductors or quantum Hall physics, things like that. And again, as you go more to the thermodynamic limit, things will scale.
Right. I guess, in the high energy case, you both want to, the reason in the high energy case, the reason that the system size grows is because you want to have higher spatial resolution or, kind of move towards continuum. And then the condensed matter is discrete to start with, but you want to go to the thermodynamic limit of system size. And it's a similar kind of demand on the resources to get to the kind of the real world questions, right?
That's correct.
Maybe a question for everybody. So, we have, two teams, one working on the gate-based implementation of this quantum simulation, another one on the analog. And, in this case, we actually didn't talk to each other until we found out that we were working on a similar problem. I'm wondering if if the projects would have come up with other questions to work on, if you had access to both digital and analog machine from the beginning, and if you pose your question with those two resources kind of at hand.
So, I mean, I can say that at the beginning of the project, we did think about how we could implement this in an analog mode. Actually, there are recent results from the Google team that are doing analog simulations where they just turn on all the couplers at once and see what happens. But it turns out that the native Hamiltonian of these Sycamore quantum processors is quite different in the C2 lattice gauge theory Hamiltonian. And for us, the gate breach approach was very natural because the structure of the circuit is very similar to the structure of the toric code circuit. So we were able to kind of leverage a lot of what the Google team has done on calibrating their devices very well to do kind of surface code memory experiments. But I think there's space to do some sort of hybrid approaches if you can find the right model.
Yeah, maybe I can just comment from the QuEra side. So at that moment, we wanted to do something with analog resources, and we're kind of lucky in some sense that this lattice gauge series emerged so naturally in this river array. So this is what allows us, because analog simulators are very powerful in the sense that they are pretty robust to errors, but they are also less flexible. So you only have a handful of Hamiltonians that you can simulate with them. And it turns out that this two-dimensional lattice gauge theory is one of them. So this is why we wanted to focus on that. But more generally, and also maybe like for the future, I think this combines very nicely with the digital capabilities also of Read atoms to, for example, introduce more complicated terms that we didn't simulate here, like plugged interactions. So this, I think, very naturally continues in a more like analog digital hybrid approach. Yeah.
And just to comment on that, as I mentioned in the beginning, QuEra does build both modes of quantum computers with neutral atoms, both analog and digital. And the digital version is something that we're hoping to launch in the next year, available to users. And we're actually looking forward to doing some of these kind of gate-based implementations of quantum simulation problems, perhaps even the continuation of this project. Now, for the people at this webinar who are maybe thinking about industry applications of quantum computers in finance, in pharmaceutical logistics, the usual suspects, do you think that there is some kind of mapping between those problems and lattice gauge theories that could be leveraged? Or where this result can be leveraged to maybe get insights on these other hard classical problems. I'm not sure if anybody has thought about this here, but I just thought I'd throw it out there as that was asked in the Q&A.
Maybe there's not necessarily a direct connection to the finance field, but you could argue that these simulations are important to develop technologies that will eventually be used in fields like that. We spoke about some superconducting exploration when we're asking some questions, and that goes to that. Understanding some of the properties of the theory helps you develop better superconductors, helps you push all kind of different advantages for different technologies. In terms of direct relationships between this models and models in these fields, nothing on the top of my mind right now.
Well, maybe this is something for us to think more about.
Yeah, I think it's an excellent question that we should all start thinking about soon, as the simulation of these models are actually possible on quantum computers.
Well, this was a fantastic session. I think that we have we have asked the kind of key questions that popped up in the Q&A. Thank you everybody for joining the Science with QuEra webinar. And this was, I think, probably our biggest list of panelists on in this webinar series, because we did bring in two teams and also both the theory and experimental aspect. So I hope we covered this topic as broadly as we could. And thank you so much for the presenters and for the participants that joined us. Have a good day.